Hello and welcome everybody. Thank you for dialing into this IMechE webinar in collaboration with Vertical Aerospace. We're excited to have you all here this evening. I hope people found it fairly easy to log on. I think we've got around 50 attendees at the moment, with perhaps a few more to join yet, so it's fantastic. I'm not sure if many people know me, but my name's Mark Bevan. I'm a fairly new member to the Gloucester IMechE committee. This being the first event that I've organised and chaired. As some of you probably know, this is actually a bit of a first for the committee as well. We've wanted to do a webinar for some time now, and we're very grateful to Vertical for agreeing to do it with us. Yeah, so it's been a bit of a strange time over the past 6 months, and it's challenged all of us in the way we do things. Aerospace as an industry has certainly not been immune and has seen quite a significant hit as a result of travel restrictions caused by COVID-19. There are a number of people which have been fortunate enough to remain busy in this period, and I know people at Vertical have been extremely busy with their recently announced developments. So putting this together was therefore a big effort on the part of our speakers today, and I'm very thankful for what has been short notice to get this prepared. So I'm thrilled to be joined this evening by Simon Harper, who is the Head of Testing and Senior Integrator at Vertical Aerospace. The talk we will show tonight is presented by Simon and his colleague James Peck, which you can see on the screen there. James is a senior vehicle architect at Vertical Aerospace. Unfortunately, James was unable to attend this evening, but we'll do our best to manage in his absence. So to circumvent any potential IT issues this evening, and to ease the burden on Simon and James a little, the talk you're about to see has been pre-recorded. Our plan for the evening will be to present this recording to you and return afterwards to answer any potential questions. Hopefully that's okay for everybody. So to submit questions, I would ask you to please use the Ask a Question function on the right-hand side of your screens. We don't have a plan to pause the webinar at any point, but please, if you think of a question during the talk, please send it to us and we will endeavour to pick it up at the end of the recording. So just to give a little bit of a background on our speakers this evening. So James is a graduate from University of Bath in mechanical engineering. He's previously worked for Caterpillar, Rolls-Royce and Alstom. He's been a key player during the formative years of Vertical Aerospace. Most recently, he's led the Seraph aircraft project and now responsible for the testing of future systems in aircraft. I will also introduce James, even though he has been unable to attend this evening. He's had a significant contribution to the talk as well. So James graduated from Sheffield University in mechanical engineering and has worked across a number of high-profile engineering projects, which include the 1.4 megawatt tidal turbine to the vectored nozzle of the VTOL variant of the F-35. He has been instrumental in the sizing and design of all of Vertical Aerospace's vehicles. Most recently, he has been working in the vehicle architecture function to help define the future vision for Vertical Aerospace's first vehicle, designed to satisfy the challenging requirements of urban air mobility. So just before we begin, I would also like to thank Ethan Tanner, the marketing coordinator at Vertical, who made this talk a possibility as well. So without further ado, I'll hand over to Simon for a brief introduction and the recording.
Mark, you there?
Can you hear us, Simon?
Yeah, hello.
Can you hear us?
Yes, I can. Can you hear me okay?
Yeah.
Yeah, I'm on my mobile. It timed out.
Ah, okay.
Start going, which is so annoying.
Oh, that's unfortunate. We thought we'd ironed out all those technical issues before, didn't we? Are you okay on there? Okay. Did you want to give a brief introduction, or did you want to just start the recording?
So you just crack on because of the issues that I'm having.
Okay. No, that's fine.
Hang on, I might be actually back online now. Let me just, I'm going to leave my phone running. I'm just going to turn my headset back on, see if you can hear me. Can you hear me? Right.
Yeah, I can hear you, Simon.
So you're still hearing me over the... Mark, you just crack on.
Yeah, you sure? Okay. Sorry about that, everyone. I'm hoping everybody can hear me as well. It's the first time we're both doing this, so it's it's new to us. Emma, I think the recording and hopefully will be sorted by the time we come to questions at the end. So everyone, please enjoy.
Hi, good evening, everyone. Thanks for joining this webinar. The presentation will be split into two. So I'm giving the first section. So I'm Simon Harper, currently head of test. I'm going to be talking over the market that we're developing our aircraft for. I'll then talk about the company's two technical demonstrators to the two aircraft that we've flown to date. Then I'm going to hand over to James Beck, our senior aircraft architect, who's going to talk more on the next step for the company, and that's our kind of certification project for our tilt rotor aircraft. I'll be around at the end of the presentation to answer any questions you have, so bear with that as we go through the presentation. I'm going to start off by talking through Vertical Aerospace's mission statement. This will give you some idea as to why we were created and what we're trying to achieve. So Vertical Aerospace believes passionately in the power of electric flight to change the way the world travels, because you shouldn't have to sacrifice the planet you live on to get from A to B. So eVTOLs, what are they and why? You've probably heard the phrase on LinkedIn. There's quite a lot of traction and press at the moment around eVTOLs, so I'll try and explain what they're all about. So the acronym's fairly straightforward. It's electronic vertical takeoff and landing aircraft. These have been around for decades. In the 50s and the 60s, there was a hell of a lot of activity for vertical takeoff aircraft. So why the resurgence now? Well, there's two main reasons for that, really. The first is development in power electronics. So some of this fueled from the electric car industry. So motors and inverters are getting smaller, they're getting lighter, and that enables them to move from the roads onto aircraft. Coupled with that is obviously battery technology. So it's increasing at a fairly steady rate, and we're now at power and energy densities that makes that technology suitable for these aircraft types. And the second kind of main technology development area is in the fly-by-wire electronics systems. So these aircraft are complex, multiple distributed propulsion systems, typically impossible for a traditional pilot to fly manually. So it needs some degree of augmentation through sensors and through flight control computers. You've all seen multi-copter drones. Essentially, we're using the similar technology, so inertial measuring systems to augment the pilot's demands to stabilize and make the aircraft safe to fly. So there's a lot happening in this section. If you have a quick search around the internet, you'll find that there's at least kind of 300 concepts in this field. So we need some degree of kind of classification of these different types of aircraft. So in the bottom left there, some of you may be familiar with the traditional VTOL wheel, often called the wheel of misfortune, because some of these aircraft were pretty experimental in their nature. Again, this was kind of some of the concepts over the last 50, 60 years of aircraft development. But the way in which they can be broken down, you can have various different propulsion systems, common propulsion systems, separate propulsion systems for propulsive flights compared to lifting. not going to spend too much time on that. The larger image here can show that these eVTOLs can be broken down using a similar classification system. So we have tilt duct, tilt wing, tilt rotor, multi-rotors, and lift and cruise aircraft. This image is a few years old, so you'll see Vertical Aerospace don't fit on here just yet, but it gives you an idea of the different aircraft out there. So I'd just like to, it's a kind of a personal bugbear of mine that these aren't necessarily flying cars. Media quite like to use that term. There are companies out there developing flying cars, but often it's a slightly compromised design because you have to meet the standards for both crashworthiness standards in particular for automotive, which makes quite a heavy aircraft. So they're often a kind of a jack of all trades type design. But I guess one more media-friendly term is electric flying taxis, which tries to give you the impression that these are on-demand, at passengers' disposal aircraft to travel them around the skies. So there's two examples shown on screen. One's SkyDrive, which have actually just completed a first piloted flight quite recently, and they're backed by Toyota. And there's another one which is a company called Aeromobile, who have had quite a few flying demonstrators. So this is new, this is novel, and there are a lot of challenges ahead of us. So I'm just going to quickly list down some of those challenges that are presented. So the first one is public acceptance. So there's potential that these things are noisy. There's the whole kind of not in my backyard objections that you may get in areas where these aircraft are utilised quite heavily. And then there's the perceived safety. So people aren't going to use these until they know that they're safe and they're proven to be safe. Second area of challenges is around infrastructure. Do we need specific vertiports? So vertiports are kind of akin to a heliport, but have the specific charging needs for these. We know that electric cars are going to become ever more common, so we need a grid that can provide the power to charge these. eVTOLs are just the same. They need quite high power to enable quick charging. And the third, and by no means least, the kind of air traffic management. So the vision is that there's going to be lots of these aircraft flying around. So it's going to be potentially congested airspace. They need to share that airspace with existing users. And it's highly likely that there's going to be smaller autonomous systems, such as survey or industrial drones, acting in that same airspace that all needs to be shared. So we need this overarching air traffic management system to ensure these are safe. So whilst we're working with partners in those areas, the focus on today's presentation is very much going to be on the aircraft. So it's providing a cost-effective, safe, and a high utilisation aircraft. So that's the focus. So here are of the 300 concepts. Some are obviously more credible than others. Just for interest, here's 4 of the competition. So on the top left, we've got a company called Whisk. Been known under quite a few different names, merged of different companies, but Kitty Hawk, Zero, Boeing now have an involvement. These were kind of funded from Larry Page, one of the Google founders, and they're currently flying autonomous demos in New Zealand, looking at the kind of passenger interaction side of things. You've got City Airbus on the top right, so they're looking at a partially ducted 8-rotored machine, and they're flight testing at the moment. On the bottom left, we have one of Beta Technologies' airframe modifications, actually, to investigate coaxial tilt rotors. They have actually moved on to a different design, which I'll cover in a minute. And then we've got Joby Aviation, who are often seen as kind of one of the prime kind of entrants in this market. So they've received $400 million from Toyota recently to help their certification efforts. They're trying to certify with the FAA in America, and they've got a 6-rotored tilt rotor concept. So of the 300 concepts, some are not as credible. Here's the flying bathtub. It just shows that there's a wide range of aircraft types out there that are being considered. It's still early days in this industry, and just starting to see some evidence of the kind of convergence of design ideas. and these typically fall into two camps. You've got the shorter range, kind of more simple aircraft, which are potentially suited for intra-city, so that's really quite short range. Not quite river hopping, but perhaps a more shuttle service. And then you've got the longer range aircraft, which tend to be winged for the increased performance in cruise. A bit faster, higher performing aircraft, but with that comes some complexity. So that's the kind of background and some of the competitors out there. I'll now kind of focus back to Vertical Aerospace. So I'm going to cover the journey so far. So Vertical Aerospace has been going about 4.5 years, maybe a bit longer. James and I were fortunate enough to join very early doors, so we were employees number 4 and 5, started in 2006. Company was founded by tech entrepreneur Stephen Fitzpatrick. So he's the founder of Bristol-based OVO Energy. And at the time that he started the company as well, he also had Manor Racing, the Formula One team. And from his kind of involvement in the energy business, and particularly the renewables focus, and seeing some of the high power technology, particularly around the hybrid powertrains that were in Formula One, he wondered if they could be merged together to form a new method of transportation. So in 2016, we were set the challenge to make the first eVTOL aircraft for the company. So that was called the POC, and I'll cover that in a little bit more detail. So in 2017, we actually had its first flight. 2018, we then put a body shell on. The company was a bit larger by that time, so about 30 engineers, rather than just the 6 engineers that designed the POC aircraft. And then in 2019, we flew our second technical demonstrator, Seraph. Its internal name is HRD, so if I inadvertently refer to it as HRD, you'll know the aircraft that I'm talking about. In 2019, we're about 70 engineers. I'm not going to cover 2020 too much. I'm going to leave that to James to kind of cover the next aircraft that we've been working on. But what I will say is now we're over 100 employees, and we're split across 2 sites in Bristol and Oxford. So in 2019, we joined forces with Mike Gascoigne Industries. So Mike's an F1 veteran really, and has brought a lot of F1 experience, supply chain, ways of working into the company to enable us to move quickly and with the newest technology. So here's the POC, proof of concept is the acronym, and it was exactly that. So there are 4 main reasons why we built the POC. One was kind of technology readiness, just to understand, our battery's good enough, our motor's quick enough, just to check the state of technology and its suitability. The next one then is multi-copter scaling effects. And this is a really interesting one. So small drones are highly maneuverable, large drones not so much. So we were trying to address some of those scaling challenges that we might have, going from grams to single figure kilos to aircraft of a ton or greater. And how do the physics stack up? The third point there is learn integration by doing. So it's often great to learn by doing. And then finally, to start developing the company's design tools and techniques. We're only six people at this time, but again, we had that eye for the future, knowing that we need to be designing a certified aircraft sometime down the line. So we need to develop those ways of working. So here's a cutaway of the aircraft, some basic kind of stats about the aircraft. With its bodywork on, it was approximately 3/4 of a ton. It was powered or kind of lifted by 4 off-the-shelf ducted fan units and motors and drive systems that were again all off the shelf. Now the battery was bespoke, so you can't get batteries of this size easily available as one-offs. So we actually chose an unusual chemistry for this battery. So we chose lithium iron phosphate, which is great for power and it's great for safety. It's not so good for energy density. So we consciously made the decision to have a reduced flight time to ensure that A, we could take off, and B, if we were to have an incident, it would be safer. The undercarriage, again, off the shelf from America, I believe. The structure was a welded aluminium space frame for lightweight. And later on in the flight test program, we installed a glass fiber cosmetic bodywork on it. And then finally, we used an open source flight control computer. So kind of prosumer grade flight control sensors that are readily available, with lots of good support as we needed. So to talk over the test approach, fairly conventional product development cycle, really. Did quite a bit of simulation up front, and a bit of subscale modelling and rig testing. And then once we had the aircraft, we did some tied down testing, some loose tether testing, and then finally some free flights of the aircraft. But it's not a purely sequential activity. We often kind of looped around some of those as we learned. So kind of one of my favourite quotes is up here. So to design a flying machine is nothing, to build one is something, but to fly it is everything, from Otto Nathaniel. He did die in a hand-built glider, but it's still a really good method there of kind of best way to learn is to build it and to fly it. So here's one of the rig tests. We tested one of the ducted propulsion units, A, to check that it matched its claimed performance, B, to look at some of the ground effects that the aircraft may have exhibited. So we had the scaffolding rig to look at the performance at various different heights above the ground. And then there you can see some of our kind of Simulink modelling that was carried out to look at load cases, to look at performance handling, to be used for pilot training in some aspects as well. We did try to get the flight physics accurately captured, but we had some challenges about getting the control laws into the simulation environment. So we decided that performing a comprehensive subscale test campaign would be really valuable to tune that flight control laws. So here's I think it's our company's second drone. It's approximately 20% scale to the full-size aircraft, and we tried to target similar centre of gravity, a similar undercarriage footprint, and get the thrust-to-weight ratios correct for both the whole aircraft and for each motor. But our biggest concern was around responsiveness. I mentioned before the scaling. The inertia obviously scales quicker than the thrust for these vehicles. So we were finding ourselves phoning motor and motor drive providers saying, we need to slow down these motor control units, whereas people often phone up and say, hang on, we want it quicker to have our drone more nimble. You can also see we've got this large kind of cruciform frame which we suspended masses on the end to again get that inertia really quite high to replicate the motion of the larger aircraft. So then we performed some tethered flights, and it was kind of three phases to that tethering. One was completely tied down, so either via load cells, so you can measure the aircraft's thrust or the centre of thrust. Then we would loosen those tethers, as you can see in this image, so that we had a few degrees of freedom for the aircraft. And we performed these in both common throttle, so we coined this the term dumb hover, where you just command a common throttle to those motors. And then we did some intelligent hovering, where the flight controller is responding to those motions of the aircraft. We did actually then venture and do a single degree of freedom tuning, where we constrained the aircraft so that it could pivot about its rear undercarriage to assess that degree of freedom's control loop. Really quite invaluable. You get to stress test all the systems whilst being at a safe distance from the ground. So off the back of that tether testing, when we had enough confidence that the aircraft would behave, we started the free flights. So we did this both indoors and outdoors to escape the weather sometimes. And we did it with and without the cosmetic bodywork. That bodywork was actually quite heavy, so we had to kind of retune some of the flight control laws whenever we installed that. So what did we learn? Kind of summarised four kind of big lessons learned from that project. One was around airframe deflections. So these need to be considered. As the aircraft stressed, obviously it would deform and resulting in different thrust vectors, which for a quadcopter like the POC can be quite significant. And then thrust to weight. So we had approximately 30% thrust overhead on each motor, and above its kind of hover condition. This was okay for control. The pilot would have liked more, really, to counteract kind of gust conditions and to be more responsive. Third point there was regarding fixed duct aerodynamics. So those ducts always remain in that orientation. There are some concepts out there that rotate them round. It's added complexity. We saw some limited kind of flight speed because of those ducts. They would try and kind of restore the aircraft to horizontal, slowing it down. And it was quite difficult to maintain the tight tip clearances that are really needed to benefit from the thrust efficiency. So fourth point was then around variable speed. So the way these multicopters are controlled is purely by changing the speed and therefore thrust on each corner to pivot the aircraft. To achieve this, you need to rapidly change that rate of thrust or speed, and that can cause quite large torque fluctuations on the powertrain. So that can result in quite a high dynamic load and oscillation on the battery system, which again is quite different from what you'd experience on a car, for example, where you've got a relatively flat, non-spiky torque demand. So next I'm just going to show a quick video of the POC flying. So this was flown at Cotswold Airport in Kemble. There is a longer video on YouTube. This is a short one. Okay, so after the POC came Seraph, or its internal name was HOD, if I accidentally refer to it as HOD. So quite a bit different from the POC, yet still a multicopter. So the key kind of design differences, it had 12 rotors rather than 4. These were actually arranged in a hexcopter configuration, although those two rotors were overlapping and contra rotating. We had a much lower disk loading, so we had more rotors, bigger rotors, so we had a payload capability, whereas the POC didn't have any. And we really wanted to start exploring what it takes to make the low voltage or the other power systems redundant in the aircraft, because this is a must for certification. So again, it was an iterative step from the POC. This wasn't necessarily meant to be a product. Arguably, it could be used for some autonomous cargo missions, or maybe that shorter range intra-city flight. But we still had our eye on a more performance-based aircraft. So the four focuses of this one then, one was to start understanding how open rotors behave, both dynamic vibrations, thrust performance, noise, etc. The second point there is redundancy testing. So this was what we referred to as the golden mission for this project, was to prove that the aircraft was capable of safe continued flight with a motor failing. I'll talk a bit more on that later. Payload capability. We have to have an aircraft with a payload capability. It's pretty obvious, and this was our first chance to look at the difference in flight behaviour with and without a significant payload. And this one's the same as the POC, but we needed to develop the company's design tools and techniques and provide validation data for some of the digital toolkits that we were using. So on top here you can see a couple of our rigs. These are simple kind of structural bend tests that we were doing. One on the wooden rotors. So we actually used laminated beech as a supplier up in Stroud that provided these for us. Some people are quite surprised that we use wood. Why not carbon fibre? It's actually quite cheap and quite quick to get hold of these rotors, but it's also a really good material. It's got a good damping properties and good damage tolerance. So the blades we selected for that reason. On the right, we're just doing some deflection testing on one of the carbon arms, taking it up to ultimate load to check that it was strong enough. Bottom left, it's a bit unclear, and apologies, the x-axis aren't quite aligned, but we were trying to focus on the motor and checking that the motor would behave as expected. So the flight controller issues a command. It wants this motor to particularly speed up. The motor in itself and the control unit there is its own control, closed loop control. So we needed to make sure that those two systems weren't fighting with each other. So we spent a lot of time ensuring that those motor units were tuned to really perform as expected. On some of the earlier runs, we were seeing kind of steady state errors and kind of creep in error over time, which wouldn't have been acceptable for flight. And then on the bottom right, again, we've got some more Simulink, Simscape simulation that we carried out to look at loads, to start investigating some of the failure cases in the safest environment that there is on the computer, before we then moved onto subscale model flights. So as before, tried to keep it as representative as possible. We put a data logger then on this scale aircraft, so we can actually extract some of that data and understand how those models compared to the real world performance. But flew indoors, flew outdoors. You can see there on the top left, we had this kind of first person camera view, and that's what the pilot was using for the flights of both the drone and the large scale Seraph. And yeah, the drone's hanging there in that gantry, and that's just us measuring its moment of inertia for scalability reasons. So once the aircraft was then built, and Seraph was ready, we performed some tethered flights. So on the left there, you can see a festive looking shot where we were tied down to the floor with some load cells. So we were again measuring the thrust margins that we had in the centre of mass. And then we moved to Llanbedr in North Wales for our flight test venue, but we also did some tie down and some loose tether testing there. So here you can see a video of the aircraft without its bodywork on. I think we had about 30 centimeters of slack in that test. So you can see that it's a little bit twitchy. It's quite a compromise. You want to ensure that your tethers are loose enough so that they don't interfere with the flight control laws, and you don't get significant snatch loads which can confuse the control system. Yeah, of course the tethers are there to protect the aircraft, so you have to make sure that the aircraft can't topple. So we went through a few different iterations of that tethering. You might notice on this video that the top frame looks a little bit wobbly. Off the back of some of this testing, we did determine that we needed to make some structural reinforcement, which significantly improved the flight performance of the airframe. And then again, once we had the confidence we were ready to go, we incrementally started the flight test campaign. So we started without any bodywork. It's the safest condition. There's less power required to hover, and we actually installed a stabilising platform. You can see there on the top left, just to give extra protection from any potential toppling issues. Bottom there, the video there, sorry, at the bottom was halfway through the flight test campaign, where we were following the centre line of the runway, and I think we reached about 70 kilometres an hour on this particular test. Again, flying at Llanbedr on one of the more sunny days that we encountered there. So what were the key lessons from that project? There was a lot about vibration, so both airframe and actually local sense of vibration. The flight controllers are quite sensitive to some of those vibrations, so good area to learn around. Coaxial rotors are pretty complex, particularly when you start considering forward flight or that kind of edgewise inflow conditions. We did do some noise surveys when we were flying, and there's one reason why we've moved away from coaxial rotors for our next aircraft design. Electromagnetic interference, so we've got a big battery, we've got high currents, going up to 600 amps in some of the bus bar arrangements. These can interfere with magnetometers. The inverters are chopping up that DC current to make an AC waveform for the motors, thousands of times a second, each one projecting some noise around the aircraft. So sensor placement, shielding, etc. was all quite crucial to really improve the performance and de-risk those systems. And then finally, powertrain. The dynamic responsiveness of that system is really quite crucial for controllability or handling qualities of the aircraft. The pilot's feedback for Seraph was that it was significantly better to fly than the BOC, partially because of that increased thrust margin. Like I say, we had about 70% rather than 30%, although admittedly most of that is for the motor out cases. But having a really rapid responding powertrain is great for flight dynamics. So here's a lovely shot of Seraph flying over the Welsh countryside. If you want to look at the kind of polished promotional video, have a look at our YouTube channel. But next I just want to show you an exclusive video that we've created to show one of the deliberate motor out cases we performed towards the end of the test campaign. Did this about a year ago, and again it was fortunate to have a sunny day at Lambeda. So here the aircraft's just yawing with the runway. The motor that you're looking at stopping is the lowest rotor nearest to us. So in the bottom right of the slide, you can see the speed traces. When this cyan line drops off, that was when we deliberately triggered the motor failure. So it happened in a few seconds. And it's about now that it's failed. So you can see it windmilling down. It never comes to a complete stop because it's still being driven by the rotor above it. There's very few failure modes that would result in a kind of a complete seizure of that rotor. But the kind of key thing to observe here is that the aircraft carried on its flight. It was very undramatic, and the pilot still had sufficient control to bring the aircraft down on the runway. We did quite a few of these tests. We did a lot more at scale through kind of more risky conditions, looking at all sorts of different permutations. But the main key here really was to get that experimental data to validate our methods. So that was a very quick summary of where we've been and how the company was created, the market that we're looking to get into, and our two technical demonstrators. I'm now going to hand over to James Peck to talk over the future.
Great, thanks, Simon. Before I do talk about the future, I think it's worth looking back again at the timeline that was shared at the beginning of the presentation. Oh, there we go. Sorry. So until recently, we've only publicly shared the work that we've been doing on multicopters, and we've actually been working on winged eVTOLs for quite some time. So whilst we only unveiled the VA1X concept a few weeks ago, this is something we've been looking at for quite a few years. So it was as early as 2018 when we first began investigating a winged eVTOL concept, and we began engaging with the EASA around October of that year. We spent a long time exploring the design space, conducting wind tunnel tests of wing-mounted rotors, and a significant number of numerical studies to identify sort of what the optimal configuration looked like. And all of this was in parallel with the Seraph program. But in 2020, we began refocusing the majority of the engineering effort into designing our first winged eVTOL prototype. And we're already a considerable way into the design of that aircraft, and we hope to show off the hardware for that prototype next year, along with demonstrating a first flight in the second half of the year. And then that will lead straight into the production aircraft and the certification program. So why the shift away from Seraph? Well, Seraph satisfies a particular market, but not the urban air mobility market, and it's that market that we really want to target. The potential for urban air mobility is huge, even today, and it's expected to grow significantly more over the next 10 to 15 years. Basically, cities are becoming larger, and there are sort of a growing number of mega cities around the world, for which the kind of existing ground-based transport options are just proving inadequate. And that's reflected in a recent resurgence of helicopter passenger flights in cities like New York, Mexico City and Sao Paulo. And incredibly, in Sao Paulo alone, there are already over 1,000 helicopter flights per day. And these are noisy, polluting vehicles based on a technology that hasn't really changed much in half a century. So recent technological advances allow for far more efficient, cleaner and quieter vehicles to solve these problems. And that opens up a potential new market where helicopters haven't previously been allowed because they've been less socially accepted because of noise. So what makes a good eVTOL concept that can compete in this UAM market? So as I've mentioned, the potential market for urban air mobility is predicted to be huge, predicted to be over 500 billion by 2040. But to have a sort of a viable aircraft that can compete in that market and have a large proportion of it, you need to have a useful range. That range needs to be sufficient to cover the major metropolitan areas, but also the commuting routes. And whilst typical mission lengths may only be in the region of 20 or so miles, there still needs to be sufficient additional range for those reserve missions. And furthermore, it's not really viable to use a large proportion of the battery charge for a single mission. Otherwise, you end up with severe battery degradation, which will lead you to replace the batteries more regularly, increasing the operating cost. Also, the more charge you use, the longer you have to spend recharging the aircraft between flights. And that means you won't be able to achieve the high utilization of the aircraft that you need to make it profitable. So that means that the actual sizing range for the aircraft needs to be considerably more than the range you typically want to fly. The next key factor is speed. And the vehicle needs to be fast enough to offer significant time savings to the ground-based motor transport. And that's also accounting for the transfer times to the vertiports. And to really open up that market, that means speeds well in excess of 200 kilometers per hour. As Simon showed in the Seraph videos, multicopters can be fast, especially when you consider that they can fly direct line of sight. I think Seraph comfortably flew at over 80 kilometers per hour, but if you want to fly much faster than that, then you begin subjecting the rotors to significant edgewise flight loads, and this increases on-board vibration and noise both on the vehicle and on the ground, which leads me on to the final point, which is noise. So these vehicles are inherently quieter than helicopters, but to really open up the potential UAM market, they need to be significantly quieter. And this is to allow the high number of flights in the urban locations, which perhaps have been restrictive of helicopter flights due to the noise nuisance. In pure hover, multicopters actually have the potential to be very quiet because of the low disk loading, the low tip speeds, and the higher frequency rotor pulses compared with a helicopter. But if you want to fly forward fast, the wake interaction from adjacent rotors quickly pushes up that noise. And in cruise, you're having to work the rotors very hard, sort of essentially supporting the weight of the vehicle the whole time. And despite the lower tip speeds in hover, again, when you start flying forward, the advancing airflow pushes up the relative velocities of the rotors, again, increasing noise. So I guess without stating the obvious, to be competitive in UAM, you need a fast and quiet aircraft with sufficient range to be useful for a wide range of routes. And to achieve that with technology available today, or even in the foreseeable future, you really can't do that with a multicopter. You need something else. And that's not to say that there isn't a market for multicopters like Seraph. Sort of the low vehicle cost and simplicity would likely make them well suited to very short range applications, and perhaps tourist flights or industrial applications. But that market's much more limited than the broader UAM market, and so not where we're currently focused. I think Seraph was a fantastic learning tool, Simon's pointed out, and its sort of elegance and simplicity meant we could get that learning very quickly. But to enter into the UAM market, it became clear that we needed a different aircraft. So I hope this chart sort of tries to explain why, but essentially to have that range and speed capability, you need good cruise efficiency. And that basically means a high lift to drag ratio, or L over D. And this chart basically shows that the higher the L over D, the greater the feasible range, but also the lower maximum takeoff weight for a given range, which is obviously a significant contributor to vehicle operating cost. And at some point, that maximum takeoff weight becomes large enough that the batteries simply can't provide enough power to get you off the ground, and it's no longer feasible. Now, for a sort of a conventional helicopter or a multicopter like Seraph, you'll struggle to achieve an L over D of much greater than 5, which with today's battery technology simply won't give you enough range to operate a UAM service. Conventional tilt rotors, whilst they're designed for speed and they're more efficient than helicopters at that speed, they still struggle to achieve a high L over D because they have heavy engines mounted on the wingtips, which puts sort of structural constraints on the practical aspect ratios of the wings. A modern GA aircraft can achieve L over Ds of between 10 and 15, and that's around about where we're targeting. We're targeting L over Ds of greater than 13, and you can only really achieve this if you generate your lift from a wing during cruise, and ideally an optimized high aspect ratio wing. So if winged aircraft are better, why isn't everyone developing them? Well, firstly, you have to carry the additional structural mass of the wing, and that can be quite significant if you intend to spend a significant time in hover. But provided your expected ConOps don't require you to spend long in hover, then the wing mass quickly pays for itself. More importantly, though, to really gain that increased performance, you need to increase the complexity, such as having tilting rotors and aerodynamic control surfaces. And that's a difficult trade because complexity drives cost, particularly in certification cost, which all needs to be accounted for in the operating models. So ideally, you want to end up with an aircraft with the best performance but lowest complexity, and that's what we've been striving for. But despite best efforts, it's inevitable that this type of aircraft is going to be more complex than a simple multicopter. And there's an assumption that some people make that simplicity equals safety, and therefore a complex aircraft will be less safe. Well, that's not always the case. I mean, modern passenger aircraft are among the most complicated vehicles ever built, and they're also among the safest. And that's because the safety has been architected into them. And that's what we've been aiming to achieve. We've designed an architecture that has built-in redundancy and high reliability despite the complexity. So here is that aircraft. Some of you may have seen this already. It's designed to carry 4 passengers and 1 pilot. And as you can probably tell, it's quite a large aircraft. The wingspan is around 15 meters, so it's notably bigger than our previous vehicles. But that size is necessary to increase the disk area of the rotors, to reduce the power and noise, as mentioned before, and to increase the wingspan to maximize the aspect ratio. There is an upper practical limit on the size to allow you to continue operations from existing heliports, and so the maximum footprint is still constrained. You can see we've got 8 rotors, 4 of which can be tilted for transition and cruise. And from a redundancy perspective, we can tolerate any single failure, be it the loss of thrust from a rotor, loss of tilt actuation, hard over control surface failures, or battery pack failures. And we're in the process of generating the evidence to demonstrate this to the authorities at the moment. You'll also notice that the aft rotors are actually 4-bladed scissoring. You might think this is unnecessary complexity, but again, this comes down to the trade of performance versus complexity. And in the case of a UAM vehicle, low noise is essential, and that drives the need for low tip speed, high solidity rotors that need to be multi-bladed essentially. But we also want to minimize drag in cruise, and so that drives the need for a system to stow the rotors. And this is an example of one of those performance versus complexity trades that we're still investigating and hope to be able to answer with the next prototype to see if we can push this design sort of further into the bottom right of that previous chart. But it's because of all this effort that we put into optimizing the aircraft, the wing loading, pylon size and shape, rotor positions and so on, that we can achieve an L over D that's comparable with a high-performing GA aircraft, which crucially gives us a viable mission range with today's battery technology. And that's important because battery technology is not advancing as fast as many people would have you believe. And furthermore, it takes many years to get that battery design certified and onto the vehicle. And we've actually already begun that process, performing a number of drop tests and flammability tests that have been witnessed by EASA. Some of the key features you'll notice on the aircraft are we have a high wing and quite large doors. And this is deliberate to make the vehicle more practical to use. If you look at many GA aircraft, getting in and out is not that glamorous. And we want a high throughput of passengers, and to make this accessible to all, So being able to get people in and out quickly and safely is again critical to this being a successful UAM vehicle. Now, I guess hopefully that's given you a very high-level insight to how we've arrived upon this aircraft. There's obviously a huge amount more for us to tell, and some great engineering that's been going on. And whilst we've tended to be quite secretive about the work that we've been doing, it's quite nice to be able to share some of that work. And I think over the next 12 months, there's going to be plenty more of it to show off. It's going to be a very busy 12 months, but that's become the norm. And even during lockdown, we've been able to make great progress with the engineering. So I'll quickly hand you back to Simon to talk about some of the test programs so far that we can share.
Excellent, thanks James. Great, thanks James. Yeah, definitely a very busy 12 months ahead of us. So the test program for VA1X is still under the definition really, but I just want to talk over some of the activities we've identified as being really crucial and have actually been going for a number of months now. So one of these is flight simulation in VR, so virtual reality. So we've partnered with Honeywell, did this a while back, for the flight control computers, and also to work on some of those flight control laws for this novel aircraft. And we're trying to target simplified vehicle operations here. So the end goal is that these aircraft might become autonomous, not needing a pilot, but there's many steps along that pathway. So to date, all of our aircraft have been remotely piloted. It's most likely for our next aircraft we're going to then have our first piloted test aircraft. But the longer term vision is that we don't need fully qualified helicopter pilots flying these things, because the economics don't necessarily work particularly well that way. So we're really keen to get our test pilots flying these simplified vehicles sooner and to get their input. Also gives us an opportunity to tune some of the pilot inceptors and really get an understanding for the handling characteristics of this aircraft. As I've mentioned before, there's that compromise between kind of power demand and the kind of handling qualities / responsiveness of the aircraft. So the image there you can see on the right is one of our test pilots flying in the simulator. We're really quite keen to use the virtual reality environment too, because it's great for confirming adequate pilot visibility. You've got the depth of vision and the kind of field of view that they need. But we're also quite keen to use that for the passenger experience. So you can see one of the virtual cabin mock-ups here. We've got the plywood out. We've made our kind of mock-ups just to check that the seating arrangements are kind of comfortable and really lend ourselves to a decent passenger experience. Throughout this talk, we've talked quite a bit about kind of noise and performance. One of the reasons why we've kind of changed to these, like James says, the highest solidarity and low tip speed rotors is to try and minimise that noise. But there's some really interesting interaction effects with the wing and with the rearward rotor. So we're doing quite a bit of scale testing, kind of quarter scale and somewhat full scale to get an idea of some of these effects. It's, in our experience, we found it's quite easy to get the performance of these, but to actually predict the noise is really quite different, so quite difficult. So we've got a few tools and methods, but we're really trying to validate those experimentally so that we've got confidence that our aircraft will be quite smooth as well. So we don't want any induced vibrations to make the kind of passenger experience not optimal. So we've already kind of started running on some testing for this. It goes without saying we'll be doing some wind tunnel testing in parallel, and James showed some of the pictures earlier on for some of the wind tunnel testing we've done to date on previous concepts. Not much to report really on the test program. It's going to be pretty similar to POC and Seraph, although more complex. This is a more complex aircraft. We've got actuated systems that we need to study. The fact that we're considering a manned flight test aircraft as well means we really need to have absolute confidence in all the systems. So more structural testing of all kind of composite joints, etc. So rigs simulation, so not just the pilot in the loop simulation, all the kind of the battery thermal simulation, etc. that needs to go on. We're putting a lot of effort to develop an automated system test bench, so typically called an iron bird, but it's an environment where we can change parameters and we can automate testing to really check that our systems, principally our avionics, that's where we're focusing on initially, are behaving. And then the flight test campaign, a little more complex this time, as the aircraft has kind of 3 modes of flight. It's got the rotor-borne or the multi-copter helicopter mode, and then it's got the conventional or the wing-borne flight. And then the third stage is that kind of boundary during transition, where you transverse from one of those flight modes to the other flight mode. So we really need to be really incremental and ensuring that when we attempt our first transition, we've got full confidence that it will be a success. That's the test program in a very, very brief nutshell. Great. Okay, so that ends the session. I mean, that was a really rapid run through of the market, the company, our previous technical demonstrators, and our next aircraft. I'm going to be around to answer any questions you may have. I'll try my best to answer them, but it's a pretty multidisciplinary area that we're after here. Excellent. Thanks again for listening.
So, there we have it. A fascinating talk. I'm sure you'll all agree. For me, it's certainly one of the most interesting areas of aerospace at the moment. So it was a privilege to hear from such an exciting company in the industry. So we'll move on to the questions now. There's been a number that have come in over the course of the recording, so we'll attempt to do our best. We'll just say at this point that the presentation will be available to download for everybody who's registered. You should receive a link to the recording, which you can download and watch again if there was any difficulties that you had with the connection or otherwise. So yeah, let's take a look at the questions. Let's check if Simon's with us. Simon, are you there?
Okay, Mark?
Yes, yeah, that's great. That's great.
Excellent. Apologies
yes, I can.
I
can.
Earlier on.
No problem. No problem. It's always to be expected as technical problems, but that's good. We've managed to resolve that now. So, excuse me. So, first question. So, it's an anonymous submission. So the question reads, as another WEAF member, it is pleasing to see such an innovative business development in the southwest of the UK. According to the website, you intend to commence the VA1X build shortly. Is Vertical in a position to engage the supply chain with local suppliers? And if yes, how should interested suppliers proceed?
Excellent. Yeah. So the answer to that is yes. We are on the hunt for suppliers, and local are preferred. Question 2: how to contact either hello@vertical-aerospace.com or contact someone like myself through LinkedIn.
That's great. That's a short answer. So on to the next one. I think these next few refer to the Seraph aircraft. So Aaron has asked, what was the primary design reasoning behind choosing 4 propellers instead of 6, as seen on the Joby Aviation design?
This is reference to the POC, so having the kind of 4 ducted units. That was selected
apologies.
for convenience, really. Yeah. We never saw that as a certifiable product, because a failure of one of those propellers or motors would be quite catastrophic. We've settled on 8. We've done quite a lot of extensive testing at scale and in simulation, and we think 8 gives us the
the best number of rotors to be tolerant of motor or rotor failure. Joby's design of 6 does also work, but it requires an active kind of yaw system to counteract some of the forces if one of the propellers were to fail.
Okay, that's great. And then the following question, so is about the load carrying capability. So is that 250 kilos, including passenger, battery, and structure, or is it just the weight of the passengers?
That's the usable payload, so that would just be passengers and luggage,
yeah,
etc.
Sure. And I probably missed it, but the question there is about the load capability in the future. So for the VA1X, what's the maximum load you're looking to achieve?
Yeah, so it's 4 passengers plus a pilot. I believe that comes in about 450 kilos.
Right, okay. Excellent. Hopefully that answers your question, Asif. So we got a question from Jim Quinn. It's to do with the control, I think, and possibly related to each of the aircraft. But the question is, how do you get it to go forwards and backwards?
Yeah, no, it's a very good question. So essentially, in hover, all the rotors are in equilibrium, and then to initiate a forward flight, you accelerate the rear rotors while slightly reducing the front rotors. That kind of rotates the aircraft nose down. It will kind of start to, very slightly drop, and then you get a thrust, resultant thrust vector from the remaining rotors as they reach back to equilibrium. So it's all via differential RPM, therefore differential thrust. The interesting one is how do they yaw, and that's by speed differential in clockwise and counterclockwise rotors to have a torque imbalance, which results in the aircraft rotating.
That's great. Just arranging some of the questions here. So the next one here is related to the sort of the technical challenges that Vertical face in attempting to begin commercial operations of the VA1X by 2024. Don't know if you've got any comments on the particular challenges that you've got there, Simon.
Yeah, hopefully we covered some of those challenges kind of over the course of the presentation. I mean, to begin commercial operations, obviously you need a certified aircraft. So that's the number one challenge is proving the design safe enough, and the test function is going to play a large part of that. There's all sorts of different areas on the aircraft that are quite novel. I guess the battery systems is one that comes to mind. Some of the other areas, such as composite structure and fly-by-wire, are fairly well understood. But this is a new classification of aircraft, and the certification guidelines and regulations are almost being written in parallel. So numerous challenges. They've got a lot of work.
Yeah, sure. That's great. So we've got a few more here. So David Ferguson has congratulated you on your great pace of progress so far. I think it's a similar question, perhaps, as in terms of the biggest obstacle that you face in scaling up. So if it's technology maturity, organizational inertia, or more external factors.
I think all three of those have some role to play. We moved particularly fast on POC and Seraph because we were sizing the designs around some off-the-shelf technology. So the motors, for example, you could get fairly quickly. That doesn't necessarily lead to an optimized product. So now we're having to develop systems to be bespoke for our needs, which obviously takes some time. We've also massively stepped up the complexity on the aircraft, which will result in a slower pace. But we still think we're pretty well structured, and we've got good skills to still move with pace.
Okay, that's great. Got a question around Uber. So Uber Elevate have announced support for the latest vertical design. Does Vertical currently have much of an appetite for an agreement with Uber or a similar company?
Yeah, Uber have been really great in getting the market out there, creating buzz. They've spoken to most eVTOL aircraft providers, and I believe we've had a few conversations. We see partners like that as potentially quite critical to establishing the market and developing some of the infrastructure. We don't yet have an agreement with them, but we're keeping an eye on their developments and using some of their kind of work and research in their white paper to kind of influence some of our design requirements.
Okay, that's great. Got a question from Raoul here. Is the certification test plan reviewed and agreed with the EASA? So presuming that refers to the VA1X.
Yeah, it would be. So the test plan, no, in short. We're working to SC VTOL, so Special Conditions VTOL, which is a bit of a mass up of kind of CS 23, 27, and 25 for some of the flight control parameters. That's published and it's been out for review and comment, as has the associated means of compliance. But those documents are still, or those regulations are still being worked on. We're quite active in the working groups that are defining those regulations. And so, strictly no, we haven't had a certification plan reviewed and agreed, but we're working very closely with the authorities. And we also have our own testing to do up front of the certification plan as well.
Okay. There's lots of questions coming in. I mean, we'll try and answer a few more, if that's okay with you, Simon. So not long ago, Vertical acquired MGI Technologies, who specialise in rapid and accurate design of composite fuselages. Can you speak about the abilities that this has afforded you in your latest development?
Yeah, awesome. So MGI, they're now Vertical Advanced Engineering. They didn't necessarily just specify composite fuselages. They were an F1 consultancy, so they did all sorts of different design jobs. They had actually had aerospace work going on before they joined the Vertical Aerospace family. So they weren't a pure motorsport background, but they just worked with such incredible pace and great skills in composites. So the bodywork for Seraph, for example, they turned around in a very, very quick time. So we're looking to kind of come to a bit of a middle ground in terms of the F1 pace and then the kind of aerospace kind of requirements-driven design. So we're looking at kind of merging those two to get through this next phase very quickly. They've also brought a load of kind of really good supply chain contacts that can help us operate with pace.
Yeah, sure. That's fantastic. So there's a question here from Mike Buxton. Which company do you think will have the first certified UAM? Is it early bird that gets the worm, or the second mouse that gets the cheese? I like that one, Mike.
Good question. In Europe, Quadcopter are doing pretty well with their, although they're quite far through with their multi-copter design. That's kind of a different market from where we're pitching ourselves, as I explained, with the kind of short range and the longer range. They've got their DOA a few months ago, so they seem to be doing quite well. And then in the States, probably Joby are pretty advanced and are very well funded, who are certifying to the FAA rules, which are slightly different to EASA. Who knows really? There's quite a few competitors in this area, and some of them still may be kind of working incognito and may raise their heads quite late in the game.
Right, okay. We'll try and answer a few more, Simon, but I can see there's quite a number there, so possibly what we could do is take those offline. We'll attempt a few more, if that's okay with you. Yeah, we've got one from Jim here, Jim Kinstone. Do you think that the higher power density of hydrogen fuel cells make these a feasible option for VTOL aircraft in the future?
Yeah, again, that's a really good question. So they're great for high energy density. I wouldn't necessarily say high power density. We've done some studies in this area, come to conclusions about fuel might needing to be liquid based rather than pressure based due to some of the tank masses. I guess ultimately we're wanting an aircraft that's fairly open to all markets. So we see that the electrical charging infrastructure is going to be ready sooner than hydrogen fuel cells. Must also add as well that you still need a large battery to couple with the hydrogen kind of power plant to deal with some of the kind of peak power demands during takeoff. So you can't get rid of batteries; they're not going to completely replace batteries. So it's definitely a technology that we're keeping our eyes on. Yeah,
that's great. So one from Kostas. As you discussed during the presentation, noise pollution is inherent with this type of technology. How does Vertical see legislation in this sector evolve as popularity with this mode of air travel increases?
that's an excellent question. Again, EASA are developing some guidelines over this. We're also considering the kind of concept of operations of these vehicles as to how we can minimise the exposure level to occupants. It's very much a work in progress, that one, but we're aware that it's one of the potential blockers for this technology. So there's a lot of focus in reducing the emissions the noise emissions of these aircraft.
Okay. So another one from Mike. What are the crashworthiness standards? Do you need stroking seats like on small helicopters?
There are crashworthiness standards kind of defined in the SC VTOL. I believe they're based around CS27 type requirements. It's worth mentioning that there are kind of two categories within SC VTOL. There's a basic and an enhanced, which has a slightly the enhanced has a kind of CS25 level reliability figure, and that's required for kind of operation over congested areas. And I believe there's different requirements for basic and enhanced. So it's loosely based across helicopter. Is the answer to that one?
Okay. There's quite a few more there.
Wow.
Yeah. Is there any that you tickle your fancy there, Simon?
I'm going to keep up. How reliable is the power source in eVTOL? That is the behaviour with respect to so many parameters like temperature. I guess this is in context of batteries. So we're doing a lot of work, and we've started engagement with the EASA very early on in this area. They are reliable batteries. They're making very good progress in EV cars. Our utilisation is quite different. So we have quite a spike in power for takeoff, and then relatively low power during cruise. We're hoping it's completely reliable. We're developing complex BMS systems to monitor the health of these cells during flight. And of course, the benefit of batteries is it's quite easy to have a modular arrangement. So if you were to have a single failure, for example, it's quite easy to then redistribute that power around the aircraft.
Okay, that's great. I mean, we're probably going over a little bit on time. If you're comfortable, Simon, perhaps what we could do is take the rest offline. We've stored those on our system, so if you've asked a question, hopefully Simon will be able to get round to answering it for you. If there's anything else you wanted to say just on that, Simon.
No, I'm happy to answer those questions, and by all means, if there's any more, reach out to me on LinkedIn. Again, apologies for the IT issues at the beginning, and potentially my 1-year-old screaming halfway through some of the pre-recorded. But thanks again for joining and taking your evening to listen to us at Vertical Aerospace.
Yeah, that's great. Just a bit of a closing statement then. So yes, a huge thank you to Simon and James as our presenters this evening, and for Simon to get through most of those questions. We've answered quite a number, I think, but people are obviously very interested. I'm sure everyone would agree. It's been really interesting from a really forward-thinking company. I hope everyone enjoyed it. So for all attendees tonight, please keep an eye out for future Gloucester IMechE events. Our next one is in mid-October, and it's based on the future of domestic heating. So it's something that's likely to affect us all in the near future, so please do join us for that. So unless, Simon, you've got anything else to add, I will say real big thank you to everyone for attending tonight. We hope to have you along again in the future and eventually back in person. Have a nice evening, everyone.